Okay, we're going to be going over the Unit 5.1 test review. So our first question, a 0.4 liter sample of gas is collected at a temperature of 45 degrees Celsius. At what temperature will the gas fill a 0.725 liter container? Okay, so what we're talking about is volume because of our liters, okay, and our liters match. Okay, so if these two are not both in the same units, you would have to do a conversion. But because they're in both liters, I'm fine. And then 45 degrees Celsius is my temperature, and it asks me at what temperature. So I'm only dealing with two properties of gas, volume and temperature, which is Charles's law. So my formula for Charles's law is V1 over T1 equals V2 over T2. Okay. So I'm going to go ahead and just plug them in to save some time rather than write them out here. So 4 liters at a temperature of 45 degrees Celsius. Well, with this temperature, I've got to convert to kelvins. So in order to do that, remember, you just take your units of Celsius and add 273 to it. So we have 318 kelvins. Okay, so volume 1 was 0.4 over my first temperature, which was 318, equals, okay, volume 2, which is 0.725 liters, and it asked me at what temperature, so I'm trying to find temperature too. So what I need to do is multiply the numbers that are across from each other and then divide that number by 0.4. So in order to plug that into the calculator, okay, I would just take 318 times 0.725, okay, and then I'm going to divide that by 0.4, which gives me, bring that back over here, I'll just round it to 2 decimals, so 576.38. We are in temperature, so I've got to go capital K for kelvins. Okay, so that's how you solve a problem using Charles's law, because the only two properties of gas that you're using is volume and temperature. Okay, your initial volume and temperature, and comparing that to the final volume and temperature. Okay, number 2, identify if the following would cause an increase or decrease in pressure in a gaseous system. Okay, so if I have an increase in the size of the container, well, if I'm increasing the size of the container, okay, so what we're talking about is volume. If it goes up, well, if we're looking at pressure, we know that volume and pressure is Boyle's law. So if volume goes up, pressure is going to go down, so we would have a decrease, okay, because it's an inverse relationship. B, more of the same gas is added to the container. So if I'm adding more gas to the same container, okay, I'm adding more particles, so we would have an increase. Okay, if I'm adding more particles, they're able to collide with each other more frequently, and so that's an increase. Increase in temperature, well, I know if I increase temperature, okay, I'm also going to increase pressure. Okay, so increase, that's due to the molecules moving faster, okay, they're gaining more kinetic energy. Also, that is, if I'm increasing in temperature, then I am doing Gay-Lussac's law. Okay, increase in temperature is going to increase the pressure. And then part D, a different gas is added to the container. Well, if I'm adding another gas, even though it's not the same, I'm still adding more particles to the container. So I'm increasing the pressure. So just kind of like this one here, if I'm adding more particles, it's causing those particles to collide with each other more frequently. So therefore, it is an increase in pressure as well. Okay, so understand the differences and the relationships of your gas laws so that you can determine if you know, some of these types of conditions would cause an increase or decrease in pressure. Okay, number 3, I've already written down the formula that you're going to use, which is Gay-Lussac's law. The question says that a steel container of oxygen has a gas, or of oxygen gas has a volume of 356 liters. If heated from a temperature of 293 Kelvin to 318 Kelvin, what will the pressure be if the original pressure was 1.2 atmospheres? Okay. So in this problem, I kind of need to look carefully. This volume could throw me off. The reason that I know that I don't have to use this volume is because it doesn't really give me a change in volume. So the volume stays the same, but it does give me a change in temperature, and it also gives me an initial pressure and wants me to find the final pressure. Okay, so that's why I'm using Gay-Lussac's law here, which is P1 over T1 equals P2 over V2, or T2. Okay, so my initial pressure, it says original pressure was 1.2 atm. All right, and then my initial temperature was 293 Kelvin. All right, I did not have to add 273 here because it's already in kelvins. Okay, that's only if I'm in degrees Celsius do I have to do some type of conversion. Okay, I want it to be in Kelvin. All right, then pressure 2 is what I'm trying to find. And my final temperature, it said it was heated to 318 Kelvin. So 318 Kelvin is going to go on bottom. All right, so I just cross multiply and divide. So I can multiply these, divide by this number. Okay, I can plug that into the calculator just like this. So I have 1.2 times 318 divided by 293, which gives me that my pressure 2, okay, that pressure 2 is going to equal, I'm going to round this to just 1.30 atmospheres, so ATM. Okay, so that's using Gay-Lussac's law to compare initial pressure and temperature to final pressure and temperature. Okay, question 4 asks, a sample of gas at 22 degrees Celsius has a volume of 10 liters and exerts a pressure of 0.78 atmospheres. How many moles of gas are in the sample? Okay, so a tip for especially this test, anytime the mention of moles in the problem, more than likely you're going to use your ideal gas law, which is your PV equals nRT. Okay, so identify what I'm trying to look for. So it's asking me for how many moles. Well, moles is represented by this lowercase n in my problem. Okay, and so in order to solve for n, I'm just going to isolate that variable. So I'm going to divide R and T, okay, to get rid of it here. Okay, so really the formula that I'm going to use, okay, from my original equation is that PV over RT equals my number of moles. Okay, so from this equation here, I can find the number of moles. So pressure is 0.78 atm, which is exactly the units it has to be in. So for ideal gas law, pressure has to be in atms. Okay, I'm going to multiply that by, okay, my volume, which is 10 liters. Okay, again, for ideal gas law, your volume must be in liters. All right, my R is just a constant, 0.0821 is those units. Okay, that's the number that you use, 0.0821. Okay, and I'm going to multiply that by the temperature. Okay, the only conversion I'm going to have to do here is that 22 degrees Celsius needs to be in Kelvin. So take 22 and add 273 to it. And so my kelvins is 295 kelvins. Okay, and so from here I can pretty much plug this into the calculator just like this. So take 0.78 times 10. Okay, and then I'm going to divide that by the bottom. Okay, but I've got to multiply the bottom numbers. So 0.0821 times 295, which gives me 0.322. I'm going to round that to 2 decimals. So my final answer should be 0.32, and N was what I was looking for. So N is the number of moles. So it's 0.32 moles should be my final answer. Okay, so that's how many moles of gas are in this sample from the problem. Okay, question 5, one of the 5 parts of the kinetic molecular theory. This comes from your very first gas law notes that we did in class. You can just pause this video here if you need to write all these down, if you don't have them in your notes. Kind of the main ones to pay attention to is that particles collide with one another in elastic collisions. So these collisions with one another and also the container that they're in is what is causing pressure to be measured. Okay. Also talking about the kinetic energy of the particles of gas. So we know that as we heat up gases, that those particles begin moving faster, so they collide into each other more, which is going to increase pressure. Okay, it's increasing, or that increase in temperature increases the kinetic energy of those molecules. So just kind of understand properties of gases and kind of what those particles are doing and how they react. If they're hotter or colder, you know that hotter gases are going to have higher kinetic energy, colder gases are going to have lower kinetic energy, and kind of how the particles respond to those things.